Today we're going to solve some exponential equations, and we're going to be looking at some that you can make the bases the same and others where you have to, bases you can't be made the same, so you're going to have to do a little bit of work with logarithms then. And first we have a couple reminders here, that reminders that if u is equal to v, then if I have b raised to the power of u is equal to b raised to the power of v, then that's a true statement because u and v are equal and b has to represent the same number. And then also, if you look down here, then we have using logarithms, that the same situation is true, that if I have the log base b of u is equal to log base b of v, then u and v have to be the same. So it works both ways. And so we're going to be using those properties to solve exponential equations today. So first of all, let's look at this one here. And whenever we can, we want to make the powers or the bases the same. So in this case, we have 8 to the power of x is equal to 2 raised to the power of x plus 1. And so what we want to do is we want to see, is there, can I change 8 to be 2 to some power? And in this case, I can say that 8 is 2 to the third power, and then I can raise that to the power of x, and I have 2 to the x plus 1. So what we'll do then is we'll use the property of exponents, which means that this has now become 2 to the 3x power, because I multiply the 3 and the x, and that equals 2 raised to the power of x plus 1. And now, since I have the same base, I can set the exponents equal to each other. So we can say then that 3x is equal to x plus 1. And now I can solve that equation. So we'll subtract x from each side. I get 2x equals 1. And divide by 2. And we get x equals 1/2. And so we have our solution. And a reminder, you should always check your answers to make sure they are correct. Okay, now we're going to look at one where the bases cannot be made the same. Here we have, we want to solve the equation 5 to the x equals 2. And 5 to the x is equal to 2. 2 and 5 don't ever go into each other, so we have to use logarithms then to solve this. And we can use natural logarithm or a common logarithm, but usually we're just going to use a common logarithm. So one of the things, a reminder, is that, remember, whatever you do to one side of an equation, you're going to do to the other side of the equation. So here we are going to take the log of both sides. So we have the log of 5x equals the log of 2. So basically all I did is put logarithm in front of both of them. Now I can use the power rule of logarithms and take that x from the exponent and move it into the front of the logarithm. And now then, to solve this equation, I just need to divide by the log of 5. And so we get x equals, and here, let me pause this just for a second. Okay, so we'll take our calculator then, and we will do the log of 2. Close the parenthesis and divide by the log of 5. And we get approximately 0.431. And so it says to confirm our solution with a graph. All right, so we will do that. Let's take a picture of our answer here first of all. All right, and we'll have that. And then we'll check graphically to see if it works. And so we'll put 5 raised to the power of x in y1 and 2 in y2. And then we'll graph them. So we'll hit zoom 6, our standard viewing window. And we can see where they intersect. So we'll hit second trace and number 5 for intersection. And when there's only one intersection point, you can just hit enter 3 times. And there we can see that graphically, we got the same answer. So in both cases, we had approximately 0.431. Now here we're going to look at example 3, which is another question where the bases are different. And this one, we're going to do this one because this one's just a little bit more difficult. And so once again, we have a base of 2 and a base of 3, and no, you can't write them with the same base, so we will, once again, we'll take the logarithm of both sides. So we have this problem here then, and we'll move the, just like we did in the last one, we'll move the powers to the front. So 4x minus 1, we found the log of 2, and 1 minus x on the log of 3. And don't forget to use parentheses there. And now what we're going to want to do is we're going to, what we can actually do is two ways. We could distribute the logs, which is one way to do it. And I think that's kind of confusing for most students. So what we're going to do is we are going to change that to 4 decimal places. So we need to find what the log of 2 is, and the log of 3. And we're going to use them to 4 decimal places for the benefit of solving this so that we're very accurate. So we have, the quantity 4x minus 1 times the log of 2, which is 0.301, and the log of 3, which is 0.4771 times 1 minus x. So we'll go ahead and distribute. So this is, let's see, 4 times 0.301 would be 1.204 minus x minus 0.301 equals 0.4771 minus 0.4771x. So now we have just a linear equation that you've seen many times before that we're going to solve. And so we're going to get the x's on the same side. So we'll go ahead and add 0.4771x to both sides. And add 0.301. So we get over here, we get 1.6. Let's see, get a 1 here. 4 plus 7 is 1. Add the 1 there, we get 8. So 1.6811x, and equals let's see, we get 0.7781. And then we'll go ahead and divide by 1.6811. Taking up quite a bit of space, that's okay. All right, so here, 0.7781 divided by 1.6811 equals, and so here's our answer. And this also says to graph it and check it, so let's go ahead and let's move this down here first of all for our answer. And let's find our problem, and let's go ahead and graph it and check it again. So in our y1, we're going to have 2 raised to the power of 4x minus 1. And in y2, we'll have 3 raised to the power of 1 minus x. And graph them. And here's our 2 graphs. Let's see, there we go. And we have 1 intersection point again, so we'll find the intersection point, and there we go, 0.4628 again. So we can see that those answers are the same, and since we did use our, so we're going to say 0.463, we'll go 3 decimal places. But by using 4 decimal places, we were actually able to get our accuracy. We still have, they're not exactly the same, but when we go to 3 decimal places, they are the same. So that's a pretty good work there. But the thing to remember is we're taking a log of both sides. Make sure then that you move the exponent to the front of the logarithm, then change the logarithms to a decimal, distribute, and then solve. All right, then we're going to look at one last example where we use substitution to solve an exponential equation. Here we have e to the x minus e to the negative x minus 4 equals 0. And what we're going to do here is we're going to stop